Okay, folks, so here we go. One of the last videos of the lecture module. Can you believe it? We're finally at the end. I can see it around the corner. I know that you can't, but I can. So here are the examples that we left off with. ABCD, and ABCD says, use an alkyl bromide and a thiol, make the following. And they give me these structures, and I told you, go take a stab and come back and check your answers to see if they're going to be correct. Okay, so let's take a look at part A. So part A was a squiggle, squiggle, and then it comes down to make an S, and then squiggle, squiggle again. Folks, this is a thioether. We talked about a thioether, and we want to know how to make this thioether. So the directions told us we had to use some type of alkyl bromide, and we had to use some type of thiol in order to get this to work. And we want to know, okay, what on earth can we do in order to get this to go forward? Okay, so let's take a look at the thiol piece first in the reagent. So this is a symmetrical reagent. It doesn't really matter which end I go on. So I'm just going to split this sulfur containing group down on the left-hand side, and I'm going to circle that piece. So this is a very good sign that that is the thiol that I need in order to make this reaction happen. So the directions told me I'm going to have to use an SH. All right, so there's the SH here on the end, and then off of that is 1 carbon, 2 carbons, and 3 carbons. So 1 carbon, 2 carbon, and 3 carbons. So that's a very good starting point. And then over here to the left, I see 1 carbon, 2 carbon, 3 carbon. So this is a very good sign that maybe, just maybe, that could be the alkyl bromide. If I can get these two pieces to come together, then what would happen is that they would join, and maybe a substitution reaction would happen where I could kick the bromine off and add on the SH instead. So the question here is, how on earth can we get this done? How can I get the thiol to react with the bromide and basically make the H leave and make the Br leave, and maybe, just maybe, end up with HBl as a byproduct? Who knows? But if I can get those two pieces off and connect the two pieces together, then I get the reagent that I'm after. So how do we do this? Well, I need the hydrogen to be removed. That's kind of our first step. So if we can go in and if we can add in some type of strong base, then this hydrogen could be picked off, and we could end up with this nucleophile that is the sulfur containing group. So that H and the OH would leave and make water. And we have this nucleophile piece that can now go in and attack the bromine and make the bromine leave. And this is exactly what happens. A substitution reaction happens at this point. So now the only thing that we have to do is mix these two reagents together. The nucleophile comes in, attaches to that carbon. The bromine takes those electrons and away it goes. And that new reagent is basically what we're after up here at the very top. So folks, that's all that we have to do. So we take a thiol. We take the thiol, we remove the hydrogen from it by using a strong base like OH, and that forms a full-blown nucleophile that we can then use and substitute in for a halogen fairly easy. All right, so the next one is this sulfur, and on one side is a methyl group, and on the other side is a zigzaggy. And then down here we have a methyl, and down there we have a methyl. So once again, I've got to figure out, what do we use? Okay, what on earth do we use? How do I split this thing up in order to get this to go forward? Well, I'm going to cut the sulfur bond on this side. Okay, I did the left the first time. I'll do it left here. We'll see what happens. If it doesn't work, it doesn't work. So if that's the case, then this sulfur has a hydrogen right there. And there's the zigzag with the two methyl groups that comes off. And there's the thiol group that the question wanted me to use. And then the piece to the left, that is a CH3 and a Br group. All right, so I do the same thing that I did with part A. I'll add a very strong base to that thiol, and that will allow me to get this negative charged sulfur that has all of the carbons that I need on it. That nucleophile will then react with that carbon, and the bond here with the bromine will leave, and a substitution reaction happens, and I will end up with the reagent that's up here at the top. Folks, it's very similar to part A. There's hardly any difference at all. Now, what if someone came around and said, well, I wouldn't have done that. Maybe I would have cut it over here. Okay, well, let's take a look. What would happen? If I cut it to the right-hand side, it's an option. Let's talk about that option. Maybe it's okay, maybe it's not. Let's talk about it. Let's discuss. That's the purpose of the lecture videos. So here I have a sulfur with a hydrogen, and on this side is one carbon. And then over on the other side, I have this carbon that has a carbon here, and a carbon down here, and a carbon down there, and I'll need a bromine at that spot. All right, so would that assembly do the same thing that the first option did? And my answer here is no. And that might not be obvious in the very beginning. However, folks, these reactions rely on an SN2 reaction. And one of the things with substitution that we ended with in Organic 1 is that substitution reactions happen. However, SN2 means that the carbon has to see two things at one time. All right, well, there's the carbon. It's seeing bromine, and this other group has to make its way in to that carbon in order to substitute it. In an SN2 reaction, that carbon has to see both at the same time. The problem is that that is a tertiary alkyl halide. And this tertiary alkyl halide does not undergo SN2. So it doesn't allow that required mechanism to take place. So this setup would not work. Now, the bromine would have to leave on its own. A carbocation would have to form, and then that sulfur-containing group could go in and then replace it at that point. However, it does require an SN2 mechanism to go forward. So because of that, that setup would not quite work. We're close, but yet not close enough. All right, so let's take a look at C. We'll use some of the same reasoning here. CH2 double bond, CH, CH, up here is a CH3 group, and then over to the side I'll have a sulfur with a CH2 and a CH3. Now that is what we want to make. Okay, so if this is what we want to make, I'm going to have to figure out how on earth can I end up with the two pieces that would allow this thing to go forward. So let's think about the other A and B choices that we did and the reasoning behind that. I know I need to break this thing up into two halves. I've got to figure out which half is the best. And we've already said that if this carbon is really cleaving at that point, and we have an alkyl halide that shows up right there, this sulfur piece is going to have to go in, and it's going to have to substitute. So here what we have is a allylic cation that begins to get formed. All right, so the best way for these sulfur reagents to happen, I'm not going to cut on the left-hand side here. I'm going to cut on the right-hand side. So what this allows me to do is do a CH2 double bond, CH, CH, with a sulfur and a hydrogen, which makes this a thiol, and my CH3 that's there, plus my other piece, which is a CH3, CH2, and then a Br. So this setup is going to be a little bit better. Just as before, I'm going to add hydroxide onto this, so that way that hydrogen can be ripped off. And when that hydrogen gets ripped off, that creates a negative sulfur, and that sulfur can drag all of the other pieces and go in and substitute onto that carbon and kick the bromine off. And then we will have the reagent up above. Okay, now, the question is, why did I choose the right-hand side and not the left-hand side? I mean, part A I did left. Part B I did the left-hand side. Well, that was because of a tertiary carbocation that's very difficult to undergo an SN2 reaction with. So why did I choose the right-hand side here as the preference? And the answer is choices. Okay? If I go left-handed, I see a carbocation that possibly could get formed here. And what do we know about delocalization? Delocalization can take double bonds and shove them in, and we get a movement of electrons that happen in this area of the molecule. And this is going to give me choices of where that alkyl halide maybe could end up and where it goes. And I don't really want that to happen, okay? I don't want to take the chance. So out of the two choices that's here, I'm not saying that this route does not work. It does. But the other route is a little bit better, because if I ensure that the sulfur is attached onto this piece right here, then I know for sure that that piece is not going to move around on me. I know no delocalization is going to happen. I know that rearrangement, it's not going to happen. So this is a surefire way that I can make sure that I'm choosing the two pieces that will, in fact, close to 100% of the time maybe, come together the way that I want them to come together. So that is why the right-hand side is a little bit better of a choice as far as the bromine goes. Remember, it's that bromine, it's that alkyl halide that's going to end up leaving. That is a leaving group, and that carbon is very special. So again, if that carbon knows that it can kind of move around and rearrange things, it could possibly do that. And this alkyl halide, because it's an alkyl halide and because it's a primary alkyl halide, we are ensuring that a SN2 reaction will take place like it's supposed to do. If I choose the other route and I put the bromine here on this side, this bromine's attached to a carbon that's on two others. This is a secondary carbocation or secondary alkyl halide, and in addition to that, it is an allylic secondary alkyl halide. So this allows SN2 or SN1 to take place. I mean, that was the thing with secondaries. We just never really knew. They were wishy-washy, flippity-floppity, and this is something that we have to watch out for. So because I cleaved it on the right-hand side, that allowed me to get the halogen onto the smaller group, I ensure that SN2 will happen, and that's exactly what I need in order for this reaction to take place. All right, so now let's look at D. We have a benzene ring. There it is. So I'm going to put a circle in there, and off of this ring, I get a sulfur. And then down here below, I have a carbon, and then that points off into another ring that has, yet again, another delocalized network on the inside. So once more, I'm looking at this molecule, and I want to know, how do I cleave this thing up into pieces? All right, so here's the thing. If I go left-handed and cleave it here, that puts a halide onto this aryl group. Folks, these things are very unstable. We talked about this in substitution. I don't know if you remember that or not, but when a halogen is directly attached to the ring like this, then we have a problem when it concerns substitution. Substitution is going to be very hard, and the reason is because I am relying on a nucleophile to come into that carbon. Well, I already have a delocalized network of electrons all the way around the ring, so that's going to push my nucleophile away a little bit. And then in addition to that, now I have this loaded bromine on that carbon, and that will push my nucleophile away even more. So this nucleophile is going to come in, and it's going to go in for that carbon, and whoop, away it goes. It's not going to stay around. So there's too many negatives, and they're too close to allow that nucleophile to come in reliably and substitute for that alkyl group. So it's just not going to work the best way that way. That means I'm going to have to cut on this side of the sulfur. So I will end up with a ring system, and that is a SH group. And then on the other side, I will have this benzene ring, and there's a carbon, and this is going to go off to my alkyl halide. So now I can ensure that this sulfur can remove the hydrogen, come into the carbon. That nucleophile is not going to be pushed away because we're off of the benzene ring. We're one carbon over, and this bromine can now leave and go make the product that I'm after. Again, what we need to add here is hydroxide for this step to work. That way I'll get the negative sulfur piece that needs to be added on to that molecule. So once more, it's all about the rules of substitution. And again, that folder is open in case you need to review the substitution reaction mechanisms. That information is all there, and I'm assuming that you are acquainted with the rules of substitution as I do these reactions, all right? Okay, so let's talk about a real sulfur-containing group, and the first one that I want to talk about is this mustard gas. All right, so mustard gas, if you're not aware, was this gas that they used way back when, and they would let everybody breathe it in on the warfield, and then they would blister up. Their skins would blister. And the reason that they would blister is because mustard gas ended up making hydrochloric acid. So literally what would happen is that the mustard gas would set onto your skin and it would absorb water. Water, of course, we are water-based creatures, and that water would be incorporated into the mustard gas, which in this case, look at this. This is a thioether. And that thioether would react with water, it would break down, and we would end up with hydrogen and chlorine, which is hydrochloric acid by definition. So literally, this was like a portable hydrochloric acid jug, and it was very concentrated. We just opened the gas up, and the gas would land onto your skin. You could breathe that gas in. There's also water in your lungs and water vapor everywhere around you, your eyes and your nose and your mouth and everywhere else. And it was just like we were dousing you with a concentrated jug of hydrochloric acid. Very painful, very cruel, but folks, this was one of those chemical warfare agents that were used in the past. It's all thioether reactions. That is why I'm bringing it up. So just to show you there is a place and there is a purpose for some of these organic compounds, whether they are good purposes like a drug, a pharmaceutical drug that really prevents an ailment or helps prevent an ailment, or something like this that was used for scientific purposes in order to create destruction and death. So this is the power of chemistry, and this is the power of organic chemistry. Now, before I stop the video, folks, there's a lot, okay? So I want you to think about Organic 1. And in Organic 1, these were the reactions that we dealt with. They were alkene reactions. They were alkyne reactions. We saw dienes as far as conjugated systems go. 1,2 addition products, 1,4 addition products. All of that was in Organic 1. And they grouped those into Group 1 for that purpose. And now what we're really talking about is a different group of compounds. And folks, all of the things that you see in that column is what we've talked about in this lecture video. And I know it feels like we've talked about all of them because this lecture's went on and on and on and on and on. Again, that's just the nature of the beast. So now we've talked about alcohols, we've talked about ethers, we've talked about epoxides, we've talked about sulfonate esters and sulfur-containing groups, and we've also talked about amines, and in this case, a quaternary ammonium hydroxide, or a quaternary ammonium period, the Hoffman reagent. So there's a lot that's going on here, and I know that, I feel that, I think that you feel that as well. So I'm going to try my best just to do a quick little snippet review, no more than 10 minutes, that wraps up hours and hours of lecture video information. So let's go through the bullet points, just to recap and review. Number 1, these alkyl halides are excellent leaving groups. So they undergo substitution and elimination very, very well. That's how we started talking about substitution and elimination. And very often we are either working with these alkyl halides in order to make them so we can substitute them later, or we are using these as reagents in these reactions that we've talked about. Next, alcohols are very poor leaving groups. so we have to activate them. We activate them by adding proton. Therefore, they can undergo substitution. They can also go elimination, but the elimination product's going to get destroyed, and that elimination product's going to go back, and then it's going to end up substituting if it didn't do it the first time. Ethers, like alcohols, are also very poor leaving groups. So we have to protonate them, just like before. Now, the way that we protonate them is a little different. That's why it says, but unlike alcohols. Remember, alcohols, we could protonate these a number of different ways. Thionyl chlorides, sulfonate esters, like the tosyl chlorides and stuff that came along, the PX3s, all of those were perfectly okay in addition to the alkyl halides. Ethers, though, we can't really do that to. It's only the acids. HX. That is the only thing that can protonate those. Epoxides, we moved on then to epoxides. They are more reactive, and the reason is because of the strain on the ring. That ring is going to open up. Two sites of attachment will be there. One will always turn into an alcohol, and the other one will end up getting a nucleophile group depending on what we add. There's also different ways that we can get these epoxides to react. And they're either going to react in an acid environment or they're going to react in a base environment. Quaternary ammonium hydroxides, these were those NH4 pluses. They undergo elimination, so those groups disappear, and this was the Hoffman that we talked about. Other than that, these ammoniums are very difficult to work with because they were once amine groups, and those nitrogens are monoamines, and they're very hard to push around. Next were the sulfur-containing groups, and those sulfur-containing groups, they are very good leaving groups, so they can participate in substitution reactions. We saw that in the alcohol reactions. And in addition to that, we can also add alkyl halides in, and they are a better nucleophile than the halides. So they can go in and substitute for the halogens as well. Another type of recap that I would like to go over is just a summary of all of these reactions. So here up at the top, we see alcohols that are reacting with acids. And here is the ranking of how fast those will go forward. Tertiaries are better than secondaries, which are better than primaries. Down here at the bottom, we have more alcohols. These alcohols are going to react with PBr3, PCl3, PI3, SOCl2s, that's thionyl chloride, and pyridine was the solvent in order to prevent the acid buildup. That's why we used that. Same type of products as up here at the top. However, no rearrangement happens down here. That was the purpose of using these. And they can only work for primary and secondaries. Tertiaries do not work with those. The other way that we could protonate or get these alcohols to do something for us was with the sulfonate esters. And that's what we saw here up at the top. So here's tosyl chloride, possibly tosyl chloride if this was a benzene ring with a methyl group. Any which way you look at this H is going to leave, and we have formed this O and S group with the double bond O, and that is a ester-containing group. Next, we talked about elimination. We said one way that we can do elimination is add acid and heat. We don't really like acid and heat that much, depending on the circumstance. Who wants to be around hot concentrated acid? That's a danger. So the other way that we could do this is use POCl3 with a little bit of stinky pyridine and keep it cold. The difference here is that POCl3 does not allow rearrangement. Sulfuric acid does. Next up was the oxidation section for the alcohol groups again. There were a couple of different ways to oxidize, and these are all primary alcohols that you're seeing on the screen. So chromic acid, chrome, can go in and create a double bond to the O. And then if it's not stopped, it will happen again, and it will make a carboxylic acid. So this first one's an aldehyde, and the second one is a carboxylic acid group. If we did not want it to go through those steps, we could use PCC. You know me. And I'm going to stop at the aldehyde. So it prevents the further oxidation from happening. If you don't like chromic acid because that is a hot hazard, environmental hazard, a health hazard, then we can use things like glacial acetic acid and a little bit of bleach. That does the same thing as PCC does, and this allows oxidation to take place, and it does not go any further after that first step. Then we talked about the Swern reaction. Same type of deal. Look at this. This is an S double bond O with 2 R's on each side. We have to get this super, super cold. And when these reactions take place, this setup is going to give me the same product as my glacial acetic and my bleach. Just a different option. Well, those were primaries. With secondaries, we could handle them the same way. And there's no difference in them except for the fact that I don't have to worry about chromic acid going again. There's no primaries involved. So chromic changes it to a ketone. There's no hydrogen there to replace again, so it stops. My PCC works the same. My bleach works the same. The Swern works the same. There's no difference. Then we moved on to the ether group, and we said ethers were very stubborn. And with the ethers, we need to look at proton or we need to look at base, acid or base. That's going to make a decision on how these things react. So if they're acid conditions, again, the hydrogen goes on here, and the oxygen leaves the more stable one behind. If they're base conditions, the base comes in first, looks for the most unstable, which would be on this side, and then allows that hydrogen to cleave in the opposite spot. Then we brought in rings, and we brought in epoxides. Here was an epoxide. We talked about adding OH and hydrochloric acid to pop, pop. On goes the OH groups in different positions if you have to worry about stereochemistry. And then if you didn't like that, you could start off with something as simple as a double bond right here and add this osmium compound. And then pop, pop, on goes the OH. They're just pointed on the same side. Down here below is a arene oxide. Remember, cytochrome P450, carcinogenic compounds. These are very bad. Not all of them, but many of them are. That epoxide ring will open up. That epoxide ring will open up in a certain way, and you do get a mix of different stereoisomers. And eventually those will settle down, and you could create these OH groups off of that as well. We then moved on to the Hofmann reaction, and the Hofmann was this amine group. That amine group was going to leave. So the base targeted a hydrogen that formed a double bond, and this nitrogen group left as a whole. So we ended up with an alkene and this tertiary, in this example, nitrogen as a product. Finally, the last one, we talked about thiols. So here we have thiols and the different types of reactions that they can undergo. Remember, I told you mercaptan was the common name because it captured mercury. And up here at the top, that's what you're seeing. So we didn't talk about this reaction. We didn't write it down. This is much later, but it gives you an idea of mercaptan. Never forget the word mercaptan. What we did talk about, though, was using sulfur as a nucleophile. So just like any other substitution reaction, sulfur goes in for the kill and it makes bromine leave. So it substitutes for the bromine. And this happens with a SN2 reaction. That's very good. That's what we want to happen. Well, if that sulfur's negative, we can still get sulfur to do its thing. This sulfur can still go in for the kill, make the iodine leave. This sulfur carries with it that extra bond and a positive charge. It doesn't lose anything. And that sulfur is okay with that because it's bigger. It can handle a charge like this. Very similar to kind of like nitrogen in a way almost, right? And then here's a tertiary sulfur that's already carrying a positive charge. Well, that's not going to work. Okay? We can't add on a sulfur again and create a +2. So there's a legitimate concern with that one. So what does happen here is that if we have a base, that base will come in and rip one of these R groups off of there, and this sulfur is remaining with the pieces that are left over. No more charge is left behind. Folks, that's it of this reaction. That's it of this section. That's it of this chapter. So I want you to know that you have went through probably about 160 to 170 slides worth of material that's in this lecture. That's craziness. Craziness. And it's a lot. So I've got good news for you. Because of the amount of reactions that take place in this lecture, you will only have a test on this lecture content. And that's it. There's so many moving parts. There's so many moving pieces. There's so many different functional groups, folks. So many different ones that we begin to see problems with the number of reactions and try to study for these, in addition to new lecture material. Who wants to do all of that? So what I want you to know is to feel comfort in that the next test will just be this lecture, and that's it. Then we'll move on and we'll look at other lecture material as we go throughout the semester. But what a way to start a semester off, right? I mean, here we're taking Organic 2, didn't really know what to expect, and then bam, 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 I hit you left and right, left again for the knockout punch. And that is with the alcohol lecture. But I warned you before this even started. So I am done. I'm done talking. I'm done. Who knows how long this has taken? 14, 15 hours worth of lecture material? I don't know. It feels like it at least. So folks, good luck on the lecture. Good luck on the assignments. Good luck on the upcoming test for the alcohols. Be prepared. Focus your studies. I'm giving you a chance to do that. It's just one chapter and that's it. But once again, it's quite a bit of material. So if you have questions, you know how to get a hold of me. If you have questions, send me an email, text me, let me know. And I'm going to try my best to use Mastering Chemistry to give you some practice problems with before the test rolls around as well. Again, Mastering Chemistry is not required. It's something that you have access to if you've purchased the tuition for the class. It's kind of all wrapped in, from what I'm told, into your tuition money unless things have changed from this point on. So you already have access. Why not use it? So go in, take a look at these problems, see what they're going to throw at you, get more comfortable with the types of questions, and that way you'll be a little bit more prepared for the test when I give it out. So until next time, my throat is going to take a rest. I'm going to take a rest, and I might need a little bit of alcohol after this lecture as well. I can already taste it. What a way to end an alcohol lecture than with alcohol itself. And I'm not promoting drinking, folks, okay? Especially if you're under the legal age to drink. Now, don't take me wrong. Don't turn me in. I'm just saying, you know? Okay, I think you've been there. I think you know what I mean. Good luck.